Let's see here. So I will make sure this thing's working. Begin here with a word of prayer. Heavenly Father, we thank you for this day. Thank you for these students, this class, and just ask that you be glorified in what we do today, Lord. In your name I pray, Lord Jesus. Amen. All right, so guys, I have also the paper attendance sheet. Maybe I've lost the other one, or maybe it's just sitting in here and I forgot to collect it last time. I don't know. Whichever. Hopefully I haven't losed it. Losed it? Doesn't seem like a word. What do you think today's date is? 8/28/24. All powers of 2 today. Interesting. I guess we'll start over here. So I wanted to, well, I'll begin by asking if there are any questions about anything in particular. But we do have time for questions pretty much every day. You just got to ask them, you know. But I have a repair to the example I did at the end of last class. Not that example. I have a different example. We'll actually be able to carry out the program I was suggesting. So I want to talk just a minute about like polar coordinate substitution. So this, the essential point here is we have, you know, like r squared is x squared plus y squared. So if you look at that, that gives us that 2r dr is equal to 2x dx plus 2y dy, right? So that's one thing we have. This is the relation between the differential of r and the differential of x and y. And you can also calculate that since theta is equal to like inverse tangent of y over x, like possibly plus a constant. This formula works in quadrants 1 through 4 modulo the place where x is 0. So that formula is mostly true. It's just sometimes the constant's 0, sometimes the constant's like plus or minus pi, depending on your choice of angle. All right? So that's the standard angle. And from this, you can derive the differential of theta is minus y dx plus x dy over x squared plus y squared. All right? So this is my my point to you guys. And so if I look at something like x times the square root of x squared plus y squared, parentheses, plus y over x squared plus y squared, parentheses dx, plus parentheses y times the square root of x squared plus y squared minus x over x squared plus y squared, all of that dy, equals to 0. Well, if you look at this, this is very much a nonlinear differential equation, right? Integrating factor method is not going to touch this thing. Separation of variables is hopeless, right? So like if you see something like this, probably changing to polar coordinates is your only hope. And so the way this goes is the following. If I change this to polar coordinates, let me kind of show you how to do it, or a way to do it anyway. So what we got here is we've got x r dx plus y r dy is equal to minus y dx plus x dy divided by x squared plus y squared. And now I'm showing you a very fast way to solve this problem. In practice, if this is a homework problem, you would have to suffer through a bunch of algebra. It would take you like an hour to solve this probably. If I was you in your place, it would take me an hour to solve this, okay? It's not an easy problem. But if I make this slick algebra move here, like so, and then I go, hey, wait a minute. This is r times x dx plus y dy. Well then, this whole equation becomes what? It becomes r dr, or r dr Sorry, that was just to say RDRR. Really, it's a dumb joke. But d theta is the other side. In other words, you get yourself an r squared dr equals to d theta. And that, my friends, come on, we can solve that, right? This is easy. So let's solve it. So I separated variables. Well, the variables were already separate, weren't they? So I integrate both sides. And this gives me 1/3 r cubed is equal to theta plus a constant. And so you don't leave your answer in r and theta, right? The problem was stated. I mean, here's the problem right here, right? This is the problem. Right? And so the solution to that is obtained by solving the r squared dr equals d theta, which gives me the solution 1/3 r cubed, theta plus a constant. Translating back into xy land, we get 1/3 x squared plus y squared to the 3/2 power equals to the inverse tangent of y over x plus a constant. And there you go. That's the implicit general solution, right? Would I ask for an explicit solution here? I mean, not if I know what's good for me, right? Can you solve for y? I can't solve for y. Right? If I take both sides to the 2/3 power, then all of a sudden I got my inverse tangent wrapped in a 2/3 power. I can't get y out of that, right? On the other hand, if I isolate the tangent and take the tangent of both sides, then my y squared is wrapped up in the 3/2 power of x squared plus y. I can't isolate the y. Yeah? But this is nevertheless a solution to this differential equation. So the kind of substitution I'm showing you here at the start of class is one where we're changing both the dependent and independent variables. So we swapped, right? X comma y for r comma theta, right? So we're swapping both the differential, so both x and y for r and theta. And when we do this, we have to trade out a differential of x and a differential of y for the corresponding differentials of r and theta. Them's the rules, all right? A lot of times, we'll look at a differential equation where we can make a substitution that keeps the x, but just trades out y for a new variable we call v. More often than not, that's the kind of substitution we look at in here. So let me show you some of those. So today I'm talking a little bit about substitutions, and of course, well, I have lots of examples today, so hopefully we'll do lots of examples. But the good news is, as we do substitutions, we will review the 3 methods that I've already shared with you guys, right? So let's see how that goes. So there are basically a couple of main examples. So here's a type of problem, so-called homogeneous first order. Has the form dy dx is equal to some function g of y divided by x. All right. This is a so-called homogeneous problem. And I say so-called because we use homogeneous to mean at least 3 or 4 different things in this class, all right? But here, homogeneous is meant to refer to the fact that this differential equation is such that if we rescaled x and rescaled y in the same way, like if I replaced x with m times x, and if I replace y with m times y, the form of the differential equation would be unaltered, right? So like there's a symmetry of this differential equation in terms of rescaling x and y. Just saying, that's the reason that this substitution works. And what substitution is that? Well, you should try a v equals to y over x substitution to solve one of these guys. All right? So I'll show you one. So example I guess this is example 2. I suppose this was example 1. I hope you guys appreciate it. It took me an hour. It took me an hour to construct this stupid thing. Because I find a way to make the, I don't know, like I told you guys, you don't have to make the problems, you just have to solve them, right? So, for the most part, x plus y over x minus y. So at first glance, this does not look like a homogeneous type problem, right? But if you try this, it's not linear, it's not separable, and I don't think it's exact either. I don't think it's exact. Is this exact? This feels like it might be exact. I'm going to chase a rabbit here for a second, guys. How do we check if it's exact or not? We got what? We have x plus y dx is equal to x minus y dy. I rewrite that in the so-called Pfaffian form. Put all my differentials on one side, right? So this is my m, this is my n, or you could say p and q if you like. We check the closed condition, yeah? So like m sub y, the y derivative is 1, versus m sub n, rather n as in nanu, not m as in mommy. Let's see here, that is minus 1. And 1 is not equal to minus 1. Oh man, it's not exact, we can't do it. Rats. Well, this is good news. So we can't, it's not linear, it's not separable, it's not exact. Our 3 methods have failed, so we must do something else. All right? So since I'm telling you this is actually homogeneous, so can you guys tell me what algebra I need to do here to make it such? Manifestly so. dy dx is equal to, let's see, how about if we take this fraction and we divide by x, top and bottom. So that gives us 1 plus y over x over 1 minus y over x. Now this is manifestly of the form I was talking about. It's a function of y over x, right? You could write this is equal to g of y over x, where like g of Pac-Man is equal to 1 plus the Pac-Man divided by 1 minus the Pac-Man. So I'm just, you know, this is just a comment. I want to point out that it now has the form. That's what I meant, right? My claim, my hint for us up at the top, if you'll allow me this insidious Carolina blue box around it. Yeah. Oh, wait a minute. Not very Carolina blue. It's kind of darker. That's what we're supposed to try. So how does that work? Another way to look at that is y is equal to vx, right? We could look at that as y equals vx. And if we do that, what's dy dx equal to? This, now here, so the substitution, what's going on here is we're trading x and y for x and v. So we're keeping x as a variable, but we're trading y out for v. So conceptually, it's a little bit different than my example 1, all right? A little bit simpler in the substitution sense. So, all right, so dy dx is, well, it's v plus x dv dx, yeah? Because product rule. All right? So that means if I want to make my substitution, I trade out this dy dx, right, for all this. So in terms of v and x, what's the differential equation I have to solve? So I'm up against dv dx. Oh, my bad. I'm up against v plus x dv dx equals to what? Equals to? Now the other side of the differential equation, we also have to convert to v, right? But we already did the algebra, so it's simple. It's just what? It's 1 plus v over 1 minus v. At this point, the substitution is done, right? We've got everything in terms of x and our new variable v. Can we solve this differential equation?
I heard a cautious yes.
Is it? It looks close to
Integrating factor. I don't know yet. I'm gonna have to work out things a bit here. So we've got x dv dx is equal to 1 plus v over 1 minus v minus v, which I think I can make a I'm gonna make a fraction out of that, right? So that's a 1 plus v minus v times 1 minus v divided by 1 minus v, make a common denominator. And anything yeah, the v's they be canceling. And I think we get a 1 plus v squared over 1 minus v. You guys, oh, I didn't write the answer down. Oh no. We'll have to figure this out ourselves. But hey, at this point, now look what we have. We have this is equal to that, right? That we can solve by separation of variables. So let's do that. So I'll bring all my variables on one side. I've got 1 minus v divided by 1 plus v squared dv, right? So what I did is I multiply by the reciprocal of this. And when I bring the x's to the other side, I divide by the x and I multiply by, I get dx over x, okay? Now, if you think I'm wrong, do jump in, all right? This is 8:15. I do make mistakes at this time. It is a documented fact. I think I can do these integrals. Yeah? What do you guys think? Let me split it up. We got ourselves like integral of dv over 1 plus v squared minus, well, let's say 1/2 of the integral of 2v dv divided by 1 plus v squared equal to, let me put this thing out of its misery. Natural log the absolute value of x plus a constant, yeah? So the first one gives us an inverse tangent of v, and this one gives me minus 1/2 the natural log of the absolute value of 1 plus v squared. I made a, let's say a w substitution. What was my substitution there? W equals to what? If I let w equal to 1 plus v squared, then like dw is 2v dv. Which is why I made that sneaky step of multiplying and dividing by 2, just to emphasize, hey, 2v dv is a dw if I make the denominator the w. So I'm making a w substitution. Oh, and we're done. Well, almost. We don't want our answer in terms of v. We'd like our answer in terms of y and x, right? We're solving a Cartesian differential equation. We'd like a Cartesian answer. So what I got here is inverse tangent of y over x minus 1/2 the natural log of 1 plus y squared over x squared equals to the natural log of the absolute value of x plus a constant. And there you have it. I would recommend not trying to find the explicit solution here. We're going to be content to have an implicit solution because the likelihood of us solving for, solving for y, pretty slim, I think. Yeah. Any questions? So if we come across a homogeneous equation, you try y over x substitution, like this, v equals y over x. There's another common type of problem I should tell you guys about. So you remember calculus 2, right? But you're like, maybe you're saying, well, I'm starting to remember. I'm like, yeah, you should start to remember. You should mature in your calculus 2 as you complete this course, because we're going to do quite a bit of calculus 2 in here. when it comes to details, right? So one of the big things in calculus 2, of course, is just figuring out what kind of substitution to make in order to do an integral, right? And if you're in my calculus 2 class, I do not tell you what substitution to make, right? It's your business to kind of have some situational awareness and understand for an integral, you make like a W substitution over there. And that's still the case in here. I do expect you can do calculus 2, and I'm not going to like coach you on the calculus 2. If you don't know it, you need to review it, right? That said, as a point of common human decency, I do not make you memorize the plethora of possible substitutions for these differential equations. As a matter of custom, and here on the test, I will tell you if it's a substitution problem, and I'll say something like, make a v equals y over x substitution. But then it's your business to complete the thought, all right? But I do that much for you. Unless it was like a bonus question, but that would be, a bonus question. If it's part of the mainstream of the test, I tell you what substitution to make, all right? The other thing I don't cover in here, just as a point of order, in the section 2.5, I think it is in the book, where they talk about integrating factors, there is a more general theorem where they talk about how to construct general integrating factors from a couple of integrals. I didn't talk about that in lecture. It's not part of this class formally. It's in the book, you can read about it. There's an example or two in my notes, but I don't press that issue. I do want you to know what an integrating factor, though, is. I want you to know how to use it and how to work it out if I tell you the general type. So an example like that we'll look at later in this class. I just wanted to make that sort of a comment. It's a comment out of place, though, because we have another substitution problem. So example, well, this is a general type. This is called the Bernoulli equation. Do you guys know who the Bernoullis were?
He was an Italian race car in Cars 2.
He was a what?
He was a race car in Cars 2.
He was a race car in Cars 2?
He was Italian.
An Italian race car in Cars 2. That's a fantastic answer.
Lightning McQueen hated him because he was faster.
Lightning McQueen's actually the villain of that movie. Let's see here.
Weren't there terrorists in that movie?
Yeah, I don't remember the movie. Anyway, I find the whole Cars franchise utterly forgettable. But v equals y to the 1 minus n. So this is a Bernoulli equation. And so the Bernoullis were like a family of mathematicians. There's like 6 of them that were, in some sense or another, like professional in their mathematics. 3 major ones that made a lot of contributions to like foundations of calculus. For example, L'Hopital's rule is likely the Bernoulli rule. It's just L'Hopital published a calculus book, and so it got to be called his rule, but it was probably like Jacob Bernoulli. It's really hard to know which one of them did which, because they kind of like had math battles amongst themselves. And it's kind of lost to history who did what first, because they would all kind of take credit for each other's stuff. But anyway, it's an interesting group of folks. This is very close to linear. This is almost a linear differential equation, see? Like if instead of being y to the power n, well, if n is equal to 1, it is a linear differential. Well, no. If n is equal to 0, no. Yes, if n is equal to 0, this is a linear differential equation, right? Because the linear differential equation has the same form with a p here and a q there, but there's no y here. All right, so if I put n equal to 0, this would be straight a linear differential equation. We know how to solve that integrating factor method, right? As we talked about last time. But this is the Bernoulli equation. It requires a v equals y to the 1 minus n substitution. So let me show you an example of how to solve this. Let me show you one we can solve. And so the example I have for us, which is example, where are we? The 3. All right, let's do it. So we're up against a dy dx plus y over x. Oh, this marker smells like death. Equals to x squared, and not in a good way, y squared, x squared. Sure, the death of your enemies. smells wonderful. Or a cat. But that's kind of a redundant statement. Let's see here. This is why I could never be a politician. Because then like 4 years later, be like, candidate Cook has said blah, 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 blah. And then I'd be like, it was sarcasm. It was sarcasm. Leave me alone. That's why I like Vance. Anyway, so this is a Bernoulli. This is a Bernoulli problem, right? Identify P is 1 over x, and you got a Q, which is x squared, okay? It's Bernoulli. N equals to what? Apparently n equals 2. Yeah, 2. Yeah, I heard it 2. So if we believe the hint, this suggests we should make a V equal to, I was about to say y, but no. What is 1 minus 2? 1 minus 2 is minus 1, right? So that's y to the minus 1. V equals 1 over y substitution. But for the sake of making the calculus easier, let's solve for y. So y is equal to 1 over v, right? In a substitution, we must trade out the formula for the differential equation, right? But that includes two different things, the algebraic part, but also the differential part, right? So we need to figure out what is dy dx in terms of dv dx. And if we differentiate this, we can get that. What's the derivative of y? We got dy dx is minus 1 over v squared dv dx, yeah? All right, so let's put that into practice over here. We got ourselves a minus 1 over v squared dv dx plus, well, as y was 1 over v, right? So 1 over xv is equal to apparently x squared over x squared v squared. If I just directly substitute in. All right. Then what should we do? Can we solve this? Thoughts?
Yes.
Prayers? What?
Yes.
Oh, prayers. Okay. No. Yes. There's a yes. How?
The x squared on the numerator and denominator cancel out, so you get 1 over v squared.
Okay. I'll allow it. Cool. Yeah. Now what?
Multiply both sides by v.
Multiply both sides by v. I like that. I raise you a v squared. Multiply by v squared. And in fact, minus v squared. Let's multiply by minus v squared. So multiply by minus v squared. What does that do for us? Cancels these guys, right? So we got dv dx, which is my preference. And then minus v over x, all right, equals to, apparently, minus 1. I'll write it out. See, I showed a step. Are you happy? I took differential equations my first semester at NC State. I was at community college for 2 years in an electronics engineering degree. And then I transferred to NC State for like electrical engineering. For my first semester, I was in electrical. I had to matriculate into it. Matriculation is this thing you do where you take courses before you're an engineer to prove that you can hack engineering courses. We should look into this. It would be helpful for you guys. But anyway, we don't do that here. Oh well. Anyway, so in my first semester differential equations class, where I met some of my best friends in college. Crazy Paul was there, Somber Paul was there. And Dr. Fauntleroy taught the class. And Fauntleroy was an interesting man. He had the voice of Morgan Freeman. Like movie quality, it was just amazing. And all of his wardrobe was still very much from the 70s, so like mostly like drawstring pants and those kind of 70s, like, you know, whatever. But invariably, he'd be teaching differential equations, and he would get to some point, and it was like 80, 90% engineering students in there because it was like transfer differential equations. And he'd get to some step, and some student would be like, "What's that?" And what did you do? What did you do? And he would invariably turn around and look at them and just go, it's just algebra, man. It's just algebra. And then he wouldn't explain, and he would go on. Which made me happy. I don't know. Maybe I'm a bad person. Anyway, so look at this we have. This is a linear differential equation in v and x. We can solve this by the integrating factor method. Right? So identify, we want an integrating factor of the exponential of the integral of minus dx over x, also known as the exponential of minus the natural log of the absolute value of x, which gives us e to the natural log of 1 over the absolute value of x, which gives us 1 over the absolute value of x. Like I said, when you get absolute value of x, drop the absolute value, just multiply by the thing. So if I multiply this by 1 over x, what do I get? I get 1 over x dv dx minus v over x squared is equal to minus 1 over x. Now, since I did my integrating factor method correctly, I can take this guy right here, reverse product rule that thing, d dx of what? V divided by x, right? The derivative of v over x gives me 1 over x dv dx minus v over x squared, because the derivative of 1 over x is minus 1 over x squared. On the other hand, I still got minus 1 over x over there. And then, a finishing blow here, integrate both sides with respect to x. And that would give me a v over x is minus the natural log of the absolute value of x plus a constant. You're wondering what I did with the minus. Minus a natural log is the natural log of the reciprocal, because the natural log satisfies the power rule, right? The natural log of a to the power p is equal to p times the natural log of a. If we have p equals to minus 1, that turns a minus out here into a to the minus 1 in here, which is why this minus log becomes log of 1 over x. It's the reciprocal rule for the log. You should know this. It's pre-calculus. Now, but many of us have forgotten it. It's okay. Now is the time to remember. Just don't forget again. Now, so what was v? V was equal to y to the minus 1. So this is, so we got 1 over xy equals to a constant minus the natural log of the absolute value of x. Is there a question?
Yeah. We were.
I was wondering how we got on the second line, I was wondering how we got x squared over x squared times v squared.
Oh, this?
Yeah.
Oh, that's just because y squared is, this y squared is, yeah. Y is 1 over xv. Oh, wait a minute.
I thought y is 1 over.
Oh, no. Oh, I'm sorry. You know what I'm thinking of? I think I'm back on this example somehow. Oh, no. Oh, man. Well, thank you, guys. Whoever noticed this like 3 minutes ago and didn't say something, how dare you? You know who you are. Ellie. Let's see here. So, it's true, isn't it? You knew, didn't you? No? All right. Let's fix this. Let's fix this. So that was just, there's no, so the x squared downstairs is only in my imagination, right? So that was supposed to be, oh man, I had such high hopes for today. X squared over v squared, which is apparently still x squared over v squared. And all that does is it puts an x squared here, which makes this an x squared, right? Which over x, minus x squared, thank you. And then this right here, then we divided by x, which gave us minus x here. Right. all the modifications are happening on the right side of the equality. Basically, I'm just multiplying the x squared after I made the wrong cancellation. So, and then that makes this not 1 over x, but minus x dx. Oh man, see? And, well, anyway. I was like, I don't remember there being a natural log in the solution. That's right, because there wasn't one. Dummy. All right, me, not you. So when I integrate, I get v over x. What? 1/2 x squared plus a constant. But v is equal to, apparently, 1 over y, right? So this means that 1 over xy is equal to, you know, minus 1/2 x squared plus a constant. Now this, as it stands, would be an implicit solution, but we can do better, right? Oh, I'm sorry, I just said do better. Almost every statement that has do better in it is it's just not a good saying. Anyway, let's put all this, let's do the algebra up here. You guys know the substitution, so I'm going to put it up here. So can we solve for y? I think we can solve this for y, right? So what I'm going to do, I'm going to start by taking the reciprocal of the equation. And that gives me xy is equal to like 1 over, you know, c minus 1/2 x squared, right? And then I'm going to divide by x. And that gives me y is equal to 1 over cx minus 1/2 x cubed, all right? Yeah, which is the answer I have in where I got this. So here you go. That is the solution to this Bernoulli problem. So the good news is if I was to put a Bernoulli problem on the test, then I would tell you make a v equals to, you know, in this case, v equals 1 over y substitution, right? The bad news is you'd have to work your way through all of that. Yeah. So I guess that's good news because it's fun. All right. Let us look at some more problems if we can. All right, so I think I've showed you the main substitutions. There are more. If you look in the missions, I think I talk about Clairaut's equation, and that one has a kind of neat solution set and so forth. And listen, there are literally, there's so many of these. There are as many substitutions as there are special differential equations. And like every little differential equation is kind of its own little world in terms of its properties and so forth. So this is just a taste of how you do substitutions. To actually know the substitution which makes sense for a given problem, that depends on the problem. And you know, it's a more complicated question than this course to figure out that in generality for sure. But there is something called symmetry methods in differential equations, which will give you a toolkit to solve those kinds of problems in more generality with understanding. But that's like past this course. But if you're interested, come talk to me. I can tell you more. Now, so here's one. So I'm going to try to do some faster examples here at the end of class. So suppose we're up against y squared plus 2xy dx minus x squared dy equals to 0. So it's not, you can't separate that. And if you tried to, it's not linear because there's a y squared. If you tried to, you know, look at this as an exact equation, you'd be stuck as well. So here's a hint. the hint is try I equals to 1 over y squared as an integrating factor. So what that means is that we multiply the equation by 1 over y squared and see what happens, right? So multiply by 1 over y squared, what do we get? We get ourselves a 1 plus 2x over y dx minus x squared over y squared dy equals to 0. All right? Now you can check the closed condition. You can check that the y derivative of this is equal to the x derivative of that. So we get minus 2x over y squared in both cases. So it's closed. Therefore, by Poincaré's conjecture, well, no theorem. Anyway, so it's closed, and we can expect then that it's exact, at least on some domain. Now, so then I need to find the potential function, right? So I'm trying to say this is, you know, partial f, partial x, and I'd like this to be partial f, partial y. So if I look at this, this tells me that f is equal to x plus x squared over y plus, you know, some constant in y if I integrate with respect to x, right? On the flip side, what happens if I integrate with respect to y? What's the integral of 1 over y squared? It is minus 1 over y, but there's a minus there, right? So that integral is literally x squared over y. And then I get some constant in x, right? And then what I do is I merge the answers, right? This is the fast way of calculating. It's not the rigorous way. The rigorous way is to take the blue answer, to plug it in here, and to work it out, all right? But sometimes we prefer speed to rigor. So that gives us here f equals to x plus y, oh, my bad, plus x squared over y is my level function, right? And you can add a constant to that, but that's the level function. Now, is that the solution? If you put a box around that and say that's my solution, I will take points off because you're wrong. That is the level function. The solution is the what? The solution is an equation which is the level curve, right? I mean, like the solution of the level curve equation. In other words, I set this equal to a constant. There you go. That would be the solution to this. That's an implicit solution. Of course, we could find the explicit solution here. What would it be? Y equals to what? So you got yourself a c minus x divided by x squared all to the minus 1 power, also known as, you know, x squared over c minus x. So there you go. There's the explicit solution, x squared over c minus x. Subtract x to the other side, flip it, multiply it. Yeah. Well, anyway, if I'm wrong, let me know. But algebra. It's just algebra. All right, I'm sorry. It's how I was raised. Another one. Let's work another one. How's about, man, where'd that problem go? I had a nice one in here. Where'd you go? Do, 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 do. Well. All right, let's try this one on for size, if I have time. Oof. Well, maybe not. Example 5. Suppose we have 2x, excuse me, I'll get it eventually here, x squared dy dx plus 2xy equal to, oh, I don't know, x hyperbolic cosine of x squared. There we go. Can we solve this thing? So one of the things I have underemphasized like a lot so far is the importance of initial conditions. We'll talk more about that like next class, all right? So what do we do here? So the integrating factor method is important, right? But sometimes it's important to jump in midstream and realize what you're looking at. See, because this is what? The derivative with respect to x of what? Yeah?
X squared y.
X squared y. Very good. That's right. So recognize your opponent, you know, there it is. And now we will integrate. And as such, the solution is x squared y is 1/2 the hyperbolic sine of x squared plus a constant. Solve for y, you've got the explicit solution 1/2x squared sinh of x squared plus the constant divided by x squared. So there you go. There's your explicit solution to this problem. All right. So start of next class, I'll probably give you guys a quiz that actually has math in it. All right. And so it will not be on substitutions because I don't want to eat all class, but I'll probably give you like, you know, a simple question or two on, you know, the kind of like separation of variables or the exact equation kind of problem we've done. All right. So things we've talked about in lecture so far. Just because I want to make sure that we're all kind of getting on the same page with things going forward. So, and then we should talk about like initial value problems, all right? So anyway, that's it for today, guys.